Day 2 on section 11.3. I can't even hardly believe that they put all this in one day because you saw how long the notes were yesterday with just the quadrilaterals and some triangles. But now we're going to do what if it's an equilateral triangle, and then we'll add some other polygons to it. Area of an equilateral triangle. There is a formula for it that we're not going to use because then that's just another formula that you have to keep track of in your head, and it's not a very friendly formula. So if you try to do this on Google and you're like, what's a formula for the area of an equilateral triangle, and they give you this, you'd be like, what? I've never seen that before. Yeah, that's because we're not going to use that. If we already know half base times height, and that's been drilled in our mind for all of elementary, middle school, and high school, then let's just use half base times height. But what we do know is that it's an equilateral triangle. But the only information they're going to tell us is find the area with a side length of 8 inches. So you know that each side is 8, which only partly helps us because all we have is the base. We only have the base. We need the height of the triangle. Well, the height, we already know from previous lesson, has to be perpendicular. So we're looking for that height. If we're looking for that height of that triangle, well then we've got to use either trig if you want to, or 30, 60, 90 triangles. And let me just give you a hint, 30, 60, 90 triangles will be faster. Remember, that's where 30, 60, 90s come from. This was 60, 60, 60. It just cut in half, so it's a 30 there, a 60 here. How big is this half of the triangle? It's 4. This half is 4. And we still need the height of the triangle. I'm not going to do this tic-tac-toe every time, but just a reminder, this is x squared of 3, this is 2x. If we know the side across from the 30 is 4, and we need the side across from the 60, that's 4 square root 3. So our height of our equilateral triangle is 4 square root of 3. Now we have a couple options here. Since we always have to cut that in half to find our height, we could just do half of our base, which is 4, times our height, which is 4 square root of 3. Half the base times the height is 8 square root of 3. Inches squared. There will be times that you'll be asked to leave it as a radical, but then there will be times that they'll ask you to go to the nearest tenth. So we'll type in 8 square root of 3, and you'll get 13.9. So the area either equals 8 square root of 3, or it's approximately 13.9 inches squared. So how are we going to do an area of an equilateral triangle every time? We're going to cut it into a 30, 60, 90 and find the pieces that we need. Okay? I know that was fast, but you have the liberty of pausing the video. If we know how to do a regular triangle, or an equilateral triangle, then we are also going to know how to do every regular polygon. You know your list. A regular polygon would be a square. You can use a square, or pentagon, hexagon, septagon, octagon, nonagon, decagon. Any of those would work. Let's do a little vocabulary first. Regular polygon has congruent sides and congruent angles. We learned that in a previous chapter. This word is new, the apothem. An apothem of a regular polygon, any regular polygon, is the distance from the center to the side. The distance from the center to the side. So in this case, our center is G, and if you're measuring the distance to the side, you have to go straight to the side. You can't just go at any angle that you want. This has to be a 90-degree angle. So our apothem in this diagram is segment GE. Segment GE is our apothem. And it says right here, it's the height of the triangle. What triangle are they talking about? Triangle that they're talking about is this triangle right here. If we can find the area of a triangle, it's not going to be equilateral, but it's going to be a triangle. If we can find the area of this triangle, then we can find the area of any regular polygon, because every regular polygon is going to be split into the number of triangles. So if we can find one triangle, then we can multiply it, in this case, times 6. If it's a pentagon, we multiply it times 5. If it's a dodecagon, we multiply it times 12. So we have to know where the apothem is measured, and then the radius, as I was saying, is the distance from the center to the vertex. The distance from the center to the vertex. So up here, that goes from G to F. So instead of going to the center of the side, it goes from the center of the polygon to the vertex. And it doesn't matter which vertex you draw it to. If it is a regular polygon, they'll all be the same length. True also for the apothem. So it's basically the side of the triangle. What triangle are we talking about? Again, if we made a triangle in the polygon, and then we could say, well, there's 6 of those triangles in there. Let me show you quick something cool about an apothem compared to a radius. Here's an apothem. I have that one in blue. If you can see that, maybe I can make it a little bit bigger. Maybe. We can twist it. There we go. The apothem in blue is the side, center to the side. And if we construct a circle using that apothem, I don't know if you can still hear me way over here. Oh, that's not good. If we construct a circle, that circle hits perfectly right in the middle of each side. So the apothem is actually the radius of a circle that fits perfectly inside the polygon, touches every side exactly in the center. So that's kind of cool about the apothem. But the radius, if I do the same with the radius, and now if I construct a circle with the radius, it made it blue instead of red, but take a look at my circle from my radius, the radius will actually be the radius of the circle all the way around, but the circle will be outside of the polygon. But each one of these, the radius to the vertex, will be the radius of a circle. Just kind of a cool thing about an apothem compared to a radius. Radius on here, I should probably have labeled it, was segment GF. Segment GF was the radius. How is that going to help us? It is going to help us tremendously once we figure out how to find the measure of a central angle. What is a central angle? I have it underlined. Each interior angle of the triangle. So what is the central angle? You're going to say, all right, if I had a center, and in this case I would have 2, 3, 4, 5, 6 sides, which means 6 triangles. How big is this central angle right here? Well, I know there's 360 degrees in a full circle if I went all the way around. If there's 360 degrees in a full circle going all the way around, then I'm going to have to divide it by 6 to find the degrees in there. So these have 60-degree angles in here. On a pentagon, if I did the same on a pentagon, there would only be 1, 2, 3, 4, 5. So I'd have to take 360 degrees and divide it by 5 angles. 360 divided by 5 is 72 degrees. Notice it got bigger because the triangles got bigger. Each of those is 72 degrees, so that is a central angle. Check out this one. I'm not going to draw it all the way around everything, but find the center, draw a triangle, count how many sides there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. 360 divided by 10 sides, the central angle is 36 degrees. Why are we going to need to know our central angles? Because guess what? There's going to be some trigonometry coming up to try to find heights and bases of triangles. And if you don't know the angles, then you can't use trig. Another one, find the center, Draw a triangle wherever. This has 1, 2, 3, 4, 5, 6, 7, 8 sides. So 360 divided by 8. These are 45-degree angles. And of course, if you needed these angles ever, you could find them. If you know the central angle is 45 degrees, these are all perfectly isosceles triangles. So you could take 180 minus 45 and cut it in half. But right now we're just concentrating on the central angles. All right, so using that information, that we can take any polygon and divide it up into triangles, we can then say that the area of any regular polygon, as long as it's regular, meaning all the triangles on the inside would be the same, would be the area half base times height. That should look familiar. That's a triangle. Half base times height, and then take it times n, times the number of sides. So if you have a regular polygon, you can just find the area of one of its triangles. Multiply times 5. One of its triangles. Multiply times 6. And we're good at finding area of triangles. Like, that's kind of easy. We know our special right triangles. We know Pythagorean theorem. We know trig. So you can find base. You can find height. You can find area of a triangle. You don't need a formula for a hexagon, and then a different formula for an octagon, and then a different formula for a pentagon. It's one formula. Area equals half base times height times number of sides. Now, if you want to cheat, or look it up, or Google it, or even look in your book, you're going to get area of a regular polygon is half of the apothem times the perimeter. But who's going to remember what an apothem is when they're trying to figure this out later? And why should we have to figure out the perimeter? That works, but we already know how to find the area of a triangle. So triangle times sides. It makes much more sense. So we're going to practice some of these. Get a calculator handy so that you can practice typing them in. A regular hexagon. So here's where it comes in handy that you know that a hexagon is a six-sided figure. The side is 10 inches. We need to find the area. Don't draw a hexagon. Draw a triangle. Draw a triangle. We know that the sides of the hexagon are 6 inches, or 10 inches, sorry. 10 inches. That's the side of the hexagon. How do I know? Because I'm not drawing the whole hexagon, but if I was going to, I'd keep going all the way around. So there's my 10 inches. I want to find the area, which means area equals half the base times the height. I'm going to continue to cut this in half and say that half of the base, I'll move my 10 inches over, half of the base is 5. So my half base is 5. All I need now is the height. To find the height of a regular hexagon, we need to know how many degrees this is up here, because we might have to use some trig, or we could use some special triangles. 360 degrees divided by 6 sides, a central angle is 60 degrees. That's what we just did in the previous problem. We know all regular hexagons have 60 degrees. So from now on, you don't have to keep calculating that. All regular hexagons are 60 degrees. So when you cut it in half by throwing a height up there, it's now 30 degrees. Oh, good. That means you have a 30, 60, 90 triangle. And we're good at 30, 60, 90 triangles. We nailed that in chapter 7. If across from the 30 is 5, across from the 60 is 5 square root 3. We don't need the hypotenuse because it's not needed over here. So we basically just took half the base, 5, times the height, 5 square root of 3. When you type that in, you don't need the extra set of parentheses. You can just type in 5 times 5 square root of 3. We're always going to have two answers. One of them exact. This area is exactly equal to 5 times 5, which is 25 square root of 3. And because it was inches, it's square inches. Then we're also going to have an approximate answer to the nearest tenth. So you'll take 25 times the square root of 3 and get 43.3. Approximately 43.3 square inches. Two answers for every problem. When they say exact, this is exact. When they say approximate or rounded, that's rounded. All right, we've got 3 more total. How about a dodecagon? Regular dodecagon, the side is 10 feet, the radius is 8 feet. There's our vocabulary word. We've got to know that. Find the area equals 1/2 base times height. Times the number of sides. Let's back up. Times the number of sides. You were probably yelling at that at me, and I couldn't hear you through the screen. Times the number of sides. So we need 5 times 5 times square root of 3 times 6. Area equals 5 times 5 times 6. It's about 150 square root of 3 square inches. Let's try this again. 150 times the square root of 3. Equals 259.8. So area is approximately 259.8 square inches. That's better because we have to get the whole entire hexagon, not just the one triangle. So with a dodecagon, 1/2 base times height times number of sides, I'm not drawing a dodecagon. It would be good to know that a dodecagon is a 12-sided figure, but I'm just going to draw its triangle. I know that it's going to keep going, 1 side, 2 side, 3, 4, 5, 6, 12, all the way around. Each side of the dodecagon is 10. So I could label these 10 all the way around. The radius, remember, goes from center to vertex. That's 8. I don't really need the 8 because it's not part of base times height, but I need the 8 to be able to find the height. Please take a look at what you have first. We have 1/2 the base, and we're looking for the height. 1/2 of the base is 5. We're looking for the height. You don't have to find the central angle. We don't need any trigonometry here. We're going to do Pythagorean theorem. 5 squared plus, I'll use h for height squared, equals 8 squared. H squared equals 8 squared minus 5 squared. 8 squared minus 5 squared is 39. And the square root of 39 is just the square root of 39. Don't round it. No decimals. So our 1/2 of our base is 5. Our height is square root of 39. And in a dodecagon, we have 12 sides. What's our actual area? 60 square root 39. And we're in square feet. 5 times 12 is 60. What is our approximate area? 60 times the square root of 39. You should be doing these on your calculator to make sure. As you can see, I make some mistakes. 374.7. 374.7 square feet. Another one, but this time it's a pentagon. Regular pentagon, they give us the apothem. We need to find the area. Area is still 1/2 base times height times number of sides. Let's draw our pentagon. Not a pentagon, just drawing a triangle. Whoops, totally missed. Just drawing a triangle. All we know is that the apothem is 8. Shoot. That's not really telling us a lot of information. We know this is going to keep going. Here's a side, 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 side. There'll be 5 sides. If the only thing that we know is that this apothem, which is the height of a triangle, is 8, we now have the height. And we know that there's 5 sides, but we do not have 1/2 the base. We're looking for 1/2 the base. One side is not enough information. We're going to need a degrees. So we need a central angle up there. 360 divided by 5 is 72 degrees. 72 degrees is the central angle. That's the whole entire angle. But we only get to use half of the angle because we can only use trig with right triangles. So now we're cutting it in half and making it a 36-degree angle. So find the central angle by dividing by 5. Find half of the central angle by cutting it in half. You're basically just working with a right triangle right now. If you don't want the whole picture, just redraw it as just a right triangle. Do some trig. This is 36. This is 8. We're looking for this. Where is that? Opposite. Where is 8? Adjacent. If it's easier to just look at a triangle the way we did trig, do it. If you're fine up here, same thing. We're looking for the opposite. We have the adjacent. We're going to be using tangent. The tangent of 36 degrees equals opposite over adjacent. This one is a cross multiply and solve. X equals 8 times the tangent of 36. You don't get to calculate that out because we want the exact answer. What is the exact answer for the area? Equals 8 times the tangent of 36 for half the base. Height is 8. Number of sides is 5. That's a lot. That's sloppy. Let's clean it up. 8 times 8 times 5 is 320 times the tangent of 36 degrees. That is our actual area of our pentagon. We found half the base to be 8 tangent 36. There's half of our base. We knew our height was 8, and we knew the number of sides was 5. Now we go with the approximate 320 times the tangent of 36 equals 232.5. 232.5. And it looks like we're in square centimeters this time. So here's the crazy thing. All I said was, you're going to just find the area of a triangle and multiply it times the number of sides. Seems easy. But it depends on what information they gave you. First information, they gave us, the first stuff they gave us a hexagon. So we had to use special right triangles. Then they gave us a dodecagon. And we had to use Pythagorean theorem because of the information they gave us. They gave us 2 sides. Then they gave us a pentagon, but they only gave us one side, and we had to figure out the angle. So there's all these different ways to find a triangle, but that's why you had to master Chapter 7 before we could do this chapter, and a little bit of Chapter 8. What if they give you a triangle that looks like this? It's like, no, I just want to do half base times height. Okay? You can't do the height of this because that's not at the halfway point. At no point did they tell you this was halfway. But you treat it just like a regular polygon. Regular polygon, area equals half base times height times number of sides. This is an equilateral triangle. So we know our number of sides is 3. We're going to turn this into a triangle. We need half its base, and we need its height. We've got its height, 3 square root 3. Whoops, I'll make that blue. We've got its height, 3 square root 3. We know the number of sides is 3. We just need half of the base. How big is half of the base? Well, remember it was an equilateral triangle, so if this whole thing was 18, half of the base was 9. So we've got half our base is 9, our height is 3 square root of 3, and there's 3 sides to the triangle. Calculate that out. Exactly 9 times 3 times 3 is 81 square root of 3, and approximately to the nearest tenth, 81 times the square root of 3 is 140.3. This did not give us a units on it, so we're just going with units squared. So, yeah, the formula's easy. Half base times height times number of sides. But you got to combine Pythagorean theorem, trig, special right triangles, apophthegms, radius. But once you continue to do the problems over and over and over, you'll get the hang of it. So don't copy them from somebody else. You'll never learn it. Good luck with that. Long notes. Sorry.